So next way you can use models is use them for predictions. Again, with this diagram here, we covered the exploration, and now you could potentially use your model to make predictions. Really when you do those predictions, it's not much different than when you do explorations. You usually start out with the exploring, and then once you understand your model and you understand your system and you believe that your model is a good approximation of the real system, you could say, well, okay, I can maybe use the model to predict what would happen in the real system. Especially if in the model you have control over everything, so you can basically do sort of what people sometimes call in silico experiments or what-if scenarios, virtual experiments. So you can run simulations that would either be impossible in the real world or too expensive or they would take too long, and in the model this is all doable in very reasonable amounts of time, and of course there's no ethical considerations that you have to pay attention to. You can just run your models. It's useful to think of the types of predictions you can make, because I think there's some where models are more suitable than others. So I capture them or classify them here in these three categories. So if you do qualitative, you're trying to predict the shape and the direction of an outcome. Sometimes for that, you don't even need a model, right? I mean, if you say, okay, if I give more drug or more vaccine, unless the drug or the vaccine is totally useless or there's some crazy interactions that could go on in the system, you expect it leads to better protection or reduced pathogen load, things like that. So sometimes you might have a model or a system that's so complex you don't even qualitatively know that, let's say you increased the rate at which the innate response is induced. Does that lead to more total killing of infected cells by T cells? Who knows? It might be complex because the innate response talks to the T cells and the T cells get activated and they kill, but then more killed cells might lead to less innate response activation, and so it's unclear what it might do, even on a qualitative level. I think where these models are really sort of ideal is this semi-quantitative. So you don't only want to predict sort of the direction, but maybe also sort of the shape of the impact. So, if you increase some parameter, does the outcome increase linearly, or does the outcome increase in some kind of saturating way, or does it go up and then maybe back down again? These kind of things, can be really hard to predict without a model, even if you kind of know what you would expect sort of qualitatively. And I think that's where models often can be useful, even if they're kept fairly simple. Now, the quantitative one, for that you need a pretty detailed model. So there you would want to basically predict the magnitude of an outcome. You'd say, let's say we double the drug dose that we give. And you don't only want to know if the pathogen load goes down, but you want to know by exactly what percentage it goes down, or exactly how many days earlier the pathogen is cleared, things like that. For that, you need models that you think are pretty realistic and can give you estimates that are precise enough that it makes sense to make quantitative predictions. And then when you do that, you usually also want to provide confidence intervals and capture the uncertainty, and we'll talk about that later today. I would say most models in immunology are not quite there yet where they can be used for that, unless it's a very specific circumscribed question. On the epi level, they're a little bit more there, though even there, I think there's a good bit of models that pretend to be quantitative, but I wouldn't actually trust their quantitative predictions because there's just too much uncertainty. So they might get sort of the order of magnitude right, but not necessarily a precise estimate yet. So just a quick example. And again, the way you go about doing predictions is exactly the way you go doing about exploration. The main difference is how you interpret it in the end. So let's assume that we think this simple model is a good approximation for some real system. That's probably not true in reality, but let's just assume we believe that there is a system where this model actually captures the dynamics detailed enough that we can use it for prediction. And so we want to know if we had some kind of drug or some intervention that could induce the immune response more strongly. So that's a parameter R here. What would happen to the peak bacteria burden? We might intuit that if we have a stronger immune response, that leads to more bacteria killing, so we have a reduction in peak, but we don't really know the shape and how strong that effect might be. So what we do is we choose different parameter values R. We keep all the other parameters fixed in this example. We run the model, then we get the time series for B. We read off the maximum from the time series and record it. And we keep doing that for different values of R. And so then we get pairs of values of R with peak B. And then we can plot that. And so there's an example of that. We have immune activation on the x-axis and peak bacteria on the y-axis. And so it behaves as we expected. Higher immune activation rate leads to a reduction. However, it's not a linear pattern here. It starts off sort of not much impact, and then it kicks in. Basically, if the immune activation is really low, then it doesn't matter. The immune response doesn't play much of a role. But once it reaches a certain level, it will control the peak. So this exact figure could be interpreted as either exploration or prediction. And that will very much depend on how much you trust your model as a good representation of the real system and you are confident that you can use it to make predictions. But the steps to go through it to get there are basically the same. Here's another example, also one we've seen before. This is from a paper on TB. And I described this before, so they ran their model. It's a much more complex model than the two equations I just showed, so it's in some sense more realistic. And then they were asking, okay, what if we could knock out these interferons, either IL-10 alone or IL-10 in combination with IL-4 or IL-12, and see what would happen to the system. And so that's what's shown here in the figure. So again, it could be interpreted as exploration. You explore the system. You say, oh, our model suggests this might happen. Let's not go and test it in some experiment. Or you could say, no, we know our model is pretty reliable, so we are fairly confident that this would actually happen. Therefore, we use that to guide decision-making, for instance, drug development. Wouldn't I say, okay, it's enough to have some kind of drug that blocks IL-10 because it reduces the bacteria load. That's the bottom right corner of the graph here. So basically the main difference is in the how you interpret or use the model results. I already mentioned that. So I think models are best used in the qualitative and semi-quantitative manner, where you can answer questions that wouldn't be obvious without a model, but that don't require completely precise predictions. If you want to make precise ones, you usually need detailed and complex models, and you need parameters or values for every parameter in your model, and that's often hard to get. And your model becomes more difficult to write and analyze. Therefore, I would always start simple, then maybe move on to qualitative and semi-quantitative predictions once you've done your exploration. And then maybe, if you trust your model enough, you can try to use it for very precise predictions. So it's, worth keeping in mind, as you build your model and analyze your model, there's always simplifying assumptions. There's no way around this. This is for every model that holds. And so any prediction depends on how good an approximation it is of the real system. And that it's not necessarily the case that a more complicated model is better. You could have a simple model. If the simple model captures the main effects, it could actually be a pretty good approximation, and you can trust the predictions. On the other hand, you can have a big, complicated model, but if it gets some of the processes wrong, the predictions are useless. So it's not necessarily model complexity alone. It's sort of how well the model captures what's going on in the real system. And there's basically the only way you can do that is through trial and error. Build a model, compare it with data, modify it, compare it with more data, and so on, until you get to a level where you think it is a very good approximation of the real system.